This is a short presentation I prepared for Dart 23. The title is Elastostatic Analysis of TSD-reported deflection slopes. When I say elastostatic, I'm referring to a pavement model that is a classic, which means that it is made of elastic layers, each characterized by a Young's modulus, Poisson's ratio, and a thickness, except for the last layer, which is a semi-infinite. And in the classic model, the loading is applied to the surface vertically, uniformly distributed over a circular area. For this presentation, I will be referring to a specific five-layered model. The first layer representing asphalt concrete with a modulus of 4,500 megapascal and a thickness of 20 centimeters. The second layer representing aggregate base with a modulus of 350 megapascal and a thickness of 20 centimeters. The third layer representing aggregate subbase with a modulus of 200 megapascals and a thickness of 40 centimeters. The fourth layer representing the upper subgrade with a thickness of half a meter and a modulus of 100 megapascal, and the fifth layer with a semi-infinite thickness representing a deep soil medium with a modulus of 50 megapascal. The loading will be modeled off MESAS, which is the TSD device owned and operated by BUST. Here is a footprint of the truck. Here you can see the rear axle, the drive axle, and the steer axle. The length of the truck is about 12 meters. There are 10 loads for the 10 wheels, numbered here 1, 2, 3, 4, 5, 6, all the way to 10. And the laser beam is placed between tires or loads 3 and 4. And here you can see the reference laser location at the offset distance of about 3 meters from the rear axle center. Specifically, the loads, the 10 loads are shown here. These are the stresses and these are the radii. They were measured from the contact width of the tires with the pavement, and here are the specific locations of the centers of the different loads. The origin of the coordinate system is in the middle between loads 3 and 4 here. So in terms of deflections, here you can see a chart showing deflection in micrometers versus offset. This is at the surface of the pavement just below the laser beam. And here is the rear axle, here is the steering axle, here's the length of the entire truck. And here you can see this solid line shows the deflection basin caused by the TSD truck. The reference laser is shown here. This is the red marker. What can be seen is you have a peak deflection around the rear axle. There's another local peak here under the drive axle, and there's another one here under the steer axle. If we were to ignore all the steer axle and the drive axle and just keep the rear axle, this would be the calculated deflection basin. And if we were to consider only the dual wheel assembly that is close to the laser beam, then this would be your deflection basin. If we calculate slopes from the model about the rear axle, and here in this chart I will show the calculated slopes versus offset with respect to the rear axle. So the rear axle is placed at an offset 0, and the positive offsets are in front of it in the direction of the truck driving, and here are offsets that negative offsets refer to points behind the truck or behind the rear axle. And this is how the slope looks like. It is not perfectly symmetric about the rear axle because at offset 0 there is a slope, and if we also consider that the TSD reported slopes take the actual slopes and remove from them the reference slope, the slope at the reference laser, then these would be the slopes reported by the device. And here you can see that at 0 offset, there is even a larger slope value. In this chart, I'm showing the sensitivity to moduli changes. The sensitivity is shown here on this axis in %, and here you can see the offsets for the lasers. What I mean by sensitivity is we take in the model E5, that's the modulus of the half space, representing a deep soil medium, and change the modulus by 1%. And observe the change in % of the different slope readings. So the laser that was at a distance of 450 millimeters behind the rear axle would experience also a change in the modulus it reports, in the slope it reports, and the change would be 0.2%. So a 1% change in E5 would generate a 0.2% in the laser in the slope reading of this laser. This is in absolute terms, so it could be that the change is a negative, but negative 0.2. And if we look at other lasers, you can see that when there's a 1% change in E5, there's less than 0.2% in the slope reported by these lasers. And if we continue to plot the expected % change in the slope reading when E5 is changed by 1%, you can see that the sensitivity is relatively low. This would be the last laser at a distance of 1.5 meters from in front of the rear axle. So just some remarks. First, I would say consider all track wheels in the modeling. This is computationally low cost because we are dealing with linear models. Also, if we were looking at linear viscoelasticity, it would still be linear, meaning that superposition can be applied, and therefore it's not expensive computationally to include all track wheels in the calculation. You could also see, as I showed here, that the deflection basin changes when ignoring some of the loads. In terms of obtaining deflections from slopes, so deflections below the TSD track are actually never zero, which means that integrating slopes to arrive at deflections works up to a constant of integration, and that constant is case dependent and not necessarily negligible. The slope asymmetry that I showed about the rear axle reflects the truck's loading footprint and also reflects the correction for a non-zero slope at the reference laser. So the point is that it doesn't necessarily indicate viscoelastic behavior. In fact, what I did here in this exercise was purely elastic analysis. The sensitivity of slopes to moduli changes. So for deep layers, I would say the sensitivity is rather low, and obviously this is case dependent. For the case I showed, and I expect that to be for all other cases, the deep layer changes would reflect very mildly on the reported slopes. For upper layers, I would say there's a medium to high sensitivity. I didn't show this, but when I say high, it means that 1% change in the modulus of a layer would generate about 1% change in the reported slope, at least in one of the lasers. Everything I have shown you here is free to share. I wrote a code inside an Excel worksheet, and you have to scan this QR code, and you can have the worksheet and play with it. Here you can see the 5-layered pavement system where you are free to change the input parameters. Here are the track characteristics. There are 10 loads considered, and here you have the positions. You have to insert the positions of the different lasers, and the calculated slopes and deflections are shown here. And here you will have the ability to do back calculation using the measured slopes. Thank you very much.